So, first off, statistics is a really big and broad field. You could potentially go ahead and get your PhD in psychology, in statistics, I mean. So, there's a lot to know, and there's very little that I can actually cover in one video, which is why I feel like the best thing I can do is to give you guys a sense of what are the kind of questions that you can ask using statistics. I'll be covering two tests today. One is called the chi-square test and the other one is called the t-test. And both of them have been extremely useful. Both of them are extremely powerful and can be used in a lot of different settings. Um, so it's important to know them, but there is a lot more to it. And if there's a certain test that you want to do, it would be worthwhile to go back and to look at the literature to figure out what the right test might be. I hope that this um, exercise at least gives you a sense of why testing is important, how what a test statistic is, and what a p-value is, and how we can interpret these values to actually make inferences on our data. And in general, what does it mean to make an inference? And we'll do all of this with Python so that you can play around with the notebook either before the session, after the session, during the session, whatever works for you. Okay. So first off, I'll refresh my kernel so that we have nothing left. You import your libraries. This is pandas, this is numpy, this is matplotlib, and this is the one that has a lot of stats in it, and this is random. So for this talk, I'll mostly be using just stats, matplotlib, and numpy. I just put pandas and random in there too. All right, so the first setup is that of binary variables, and the test that I'm going to look at is called the chi-square test. And one setting where this could be applied could be as follows. Suppose you're comparing two students and they have answered multiple choice exams with different marks. So suppose you are one student and you've gotten 82, your other friend has gotten 87, and you're wondering whether or not there's actually a difference. So the question is there a difference in ability? Suppose you're concerned about whether a certain food item is associated with the higher risk of cancer. So 1,000 people eat the food regularly, of them 100 of them have cancer, and say something like 1,200 people, a lot of people don't eat this food regularly, and you know this is 10%. I'm saying that maybe a little lesser, 900 of them have cancer. So the general setup is that you've got a binary outcome, a yes no variable. Over here, the yes variable is answer is correct and answer is wrong. Over here, the yes variable is has cancer, does not have cancer. And you're concerned about whether the probability of success is greater in condition 1 or condition 2. In this setup, the condition 1 is person 1, like their answers. Condition 2 is the person 2. Over here, condition 1 is people who eat this food regularly, and condition 2 is people that do not eat this food regularly. So instead of using a known data set, I've decided that we could instead use simulations. The advantage of using simulations is that you can play around with these numbers and get a sense of what's going on too. Okay. So these are called random seeds. I'll not talk about them too much. I mean, they basically make sure that if you run a certain random sample, it will generate different values. So for example, if I have random.random, this is how I generate a random number. It is this value, and now if I generate it again, it'll be a different value. But if I seed it all the time, then I'll always get the same value. So that's the reason that I've seeded it, so that this notebook sort of has the same values that I've used, and it doesn't change based on the run. Right? So here I'm drawing binomial variables. So this means that the probability of a certain success is say 8.8, so that is 80%, and there are 30 trials that are being done, and we do the same process 15 times. So with an 80% success, you get around 80% every time. So 25, 23, 30, 25, 26. But you see there is some variation. So every time you sort of draw a random variable, it's a little different. If the probability of success is 0.7, each of these numbers are slightly smaller than the numbers on top, right? So there's variation over here and there's variation over here. Now, what we are interested in is sort of trying to say that this is generated with 0.8 and this is generated with 0.7, and that this is lesser than this. So the probability of success in this condition is lesser than that of this condition. And if you directly compare the values, on the whole, that seems to be the case, except for this, say, the second last value, where even though the probability of success is lower over here, just because of random variation, the number is higher than that over here. So that's the kind of thing that we want to avoid. That is why we have to use statistics, right? So do we have enough samples to sort of actually say that these two numbers are different, right? So what I've done over here is, so once again, this is a binomial random variable. This is the probability of success, and this is the number of trials. This is the number of outcomes that are done. So over here, we've got 300 trials, probability of success is 0.8. And then the second set, you've also got 300 trials and probability of success again is 0.8. So success 1 is this number, success 2 is this number. And let's say I run this thing. The numbers are a little different. So in the first case, you have 238 out of 62, out of 300 successes. In the second case, you got 243 out of 300 successes. So these numbers are actually different, even though the underlying probability that generated it is the same. So now when we actually statistically test for difference, we should get the answer that there is no difference. Okay. So this is how you actually run the test. It's really simple. But before running the test, you have to make sure that your data sort of looks correct. So this is the number of successes. This is the number of failures. Number of failures is number of trials minus the number of successes. And this is the second set, number of successes, number of failures. I put them all in a 2x2 table, and this is what the table looks like. This is what I was mentioning slightly a little earlier. And then this is how you run the test. It's really straightforward. You just put it into this chi-square thing, and here you get the results. Okay, so you have to interpret these values. That's what it's about, right? So I've opened these values up over here. So this is test statistic, p-value, degrees of freedom, and expected. So expected is that if they had the same probability, then what would we have expected, which is this. And then the question that they ask in the chi-square table is whether this is significantly different from this. If it is, then the test value will be high. If the test value is high, the p-value has to be small. So test statistic, I'll write this over here. This value is high when expected is different from the contingency table I mentioned above. And it is small when they're similar. Now, if you were doing this statistics with your own hand, you'd sort of have to look at this and look at the degrees of freedom, and then open up your table and figure out what the p-value is. But all that this function does sort of is that it just calculates a test statistic and it drops out the p-value. Now with the p-value, if the p-value is small, then it means that it cannot be explained by chance. Okay. If it is large, then it can be explained by chance. So what this says is, so the p-value is, the idea of the p-value is, um, so with this test, so this is small and large, right? Now the question is, how small and how large does it need to be? And the way they decided that was that they sort of run random samples several times, and they'd see how large does the test statistic become under randomness. Okay. And so the p-value, usually the values that people use is either 0.05 or 0.01. So this 0.05 means that if these two values were the same and you ran samples random times, then 1 in 20 times you'd get a significant result. All right. So let me repeat that in this case, for example, we've got 300.8, 300.8. Let's say I keep doing this, right? Then my p-value keeps changing. Every time I do the same test, the p-value changes, right? Your observations also change, right? So if this p-value is smaller than 0.05, that means that it cannot be explained by chance as much. It just means that there's a 1 in 20 chance that this p-value is so small if this was by chance. Okay. Let me give you an example of when I actually make the probabilities different, right? So in all of these cases, the p-values were actually above 0.05. You see, it's 0.01. Now, almost anytime I do this, it'll always be pretty small. And the test statistic is pretty large. So this larger test statistic, but in this case, for example, even though these two are different, these two observations are pretty close to each other. So it's possible that these two observations were actually generated by the same underlying probability, which is why you have such a high p-value. Okay. But usually the p-values will be quite different. You see, it's different again. It's pretty small now. Okay. So I'll let you play around with this. You can have, say, something that's even closer. If you have that, then you see your p-value is not going to be, even though they're different, right now it's lesser than 0.05, but you see now there's no difference. It's almost the same in this outcome. Right? So now again, the p-value is insignificant. The way you sort of make the p-value significant is by increasing the number of trials. So let's say I had 3,000 trials, right? Then I'd be able to catch this 0.05 difference in probability. You see, now the p-value is suddenly significant. I can do this all the times, and you see it's really small. Now it's 0.005, right? So it's okay. So from a programming perspective, all that you sort of need to know is how to put in this contingency table. Now for future cases, so in this case, we have two outcomes, yes or no, and you have two conditions, one or two, right? You can also have three conditions with three outcomes, and in that case, our contingency table will be a little larger. It'll be a 3x3 table. So in general, with chi-square, if you have n conditions and you've got m different outcomes, you can test if there is a difference in the probability of anything, of basically any difference being there in that entire table. And you put it all in the same sort of a contingency table with condition 1 and outcome of type 1, condition 2, outcome of type 2, and then you just run this stats.chi2 contingency and you get your results out. One simple rule of thumb is if you just manage to get this contingency table and this p-value is lesser than either 0.05 or 0.01, then that means that it's different. In biology, in psychology, in many of these fields, this is the sort of bar for p-value. The criticism against this is that you can obviously make your number of trials pretty large, and under those large conditions, you'll be able to pick a small enough difference. So people run simulations in what's called power tests to figure out how many trials they would need to run to actually pick up a certain size of a difference. This test has limitations, like this test is not very useful if you have very few trials. You can't tell much. You need, say, something around 30, a little more than 30 trials to actually start running such a test. Yeah, so this is the chi-square test. As a quick recap, this test is applicable when you have, say, a binary outcome variable, which is either success or a failure, and you're concerned about whether that success is greater in condition 1 or condition 2. The way you run this test is by taking the successes, the failures that you have, and then putting them in this 2 by 2 table. Then you run this one command, stats chi-square contingency, as a 2 by 2 table. You get these different numbers out. These numbers are the test statistic, the p-value, the degrees of freedom, and the expected. The expected is under the assumption that there is no difference between these two. What should we have seen? The degrees of freedom is a function of how many columns and rows you have over here. The test statistic is a measure of how different it is, how different the observed is from the expected. And the p-value is a measure of just how special this test statistic is. So this test statistic is extremely large, then you can't explain it by chance. All right. Okay. So this is for binary variables. You can run similar tests for continuous variables. And the test is called the t-test, and it's called the independent samples t-test. You have similarly a dependent samples t-test, which I'll tell you about towards the end. The general setup for this is, one example for this is the heights of men greater than that of women. So, you could go around looking at men's heights, and you'll have a certain distribution. You could go around asking women for their heights, and you'll get a certain distribution. There's an overlap between these two distributions because there's some women that are taller than the short, like the taller women, are taller than the shorter men. But at an average, men are say taller than women, right? So, general setup is that you've got continuous set of values in condition 1, and you have another continuous set of values in condition 2. So this is what we're going to be using for a simulation. So I'll just start off with like the x, which is -5 to 5. I'll draw samples from a normal distribution. So these are two normal distributions. One is blue and one is orange. The center of the blue one is at 2, and the center for the orange one is at 1.5. And these are these vertical lines. So as you can see, the means of these two distributions are actually different from each other. So in this question, the question that we are asking is not, is the heights of men greater than women? The more specific question is the mean height of men greater than that of women? Then let's clarify, the mean height of women. Right? So you can draw samples from this normal distribution, and what you'd get is something like this. Right? So even though this is your distribution and this is clearly on the right of this one, you can, so this is once again, so this is the stats normal distribution. Location is 2, scale is 1, which is the standard deviation, and this is the PDF, which is the probability density function, which tells you just how likely it is for you to like draw a value from a certain point. So if the PDF peaks at point 2, at 2, it means that 2 is sort of the most likely sample to draw. Okay. So, all right. So even though say this is my distribution, my samples do not exactly follow that distribution. It's a little messy, it's a little noisy, it's a little around these things, which is why I may not have, you may have quite a large overlap between these two. And if you were to actually look at these values, you may not be able to tell whether they're actually different from each other or not. They may actually look pretty similar. So you see, look at these two values. These 2.4, 1.9, 1.9, 1.3, 3.1, 2.4. So they look pretty similar. This one's higher than this one, but there are lots of 2s and 3s over here. There are also lots of 2s and 3s over here. There's some 0.1s, right? Which is basically what we'll see in our plot, right? So they have a very large overlap, but the means, even in these samples, are sort of different from each other. So you take all the random vals, which is my random values over here, which are these values, and I take random vals too, which are all of these values, and I want to test if they are different from each other. Now the way I test whether they're different from each other is this test: stats.t-test independent random vals too, and in the results I get the t-value and the p-value. This is the t-value. Once again, like the test statistic mentioned upstairs, if this value is large, it indicates that it is significant. However, just how large is determined by its p-value. Its p-value needs to be small. And if it is once again lesser than 0.05, then it cannot be explained. If it's lesser than 0.05, then people usually say that it cannot be explained by chance. It is random. So in our case, our p-value is much lesser than 0.05, which is why it cannot be explained by chance. And let me give you another example of where these two actually overlap with each other. In this case, you see, the sample means are very similar. Although the distributions are a bit different, the sample means are almost perfectly on top of each other. So my t-value is 3 and my p-value is still significant. So this means that it is able to still capture this difference. I'm not sure if that actually worked correctly, but now it's working. So the random vals and random vals 2 is my result. My t-value is pretty small and my p-value is also pretty small. It's pretty large. It's 0.47. 0.05 was our cutoff. I could do this again. Now my t-value is 1.2 and my p-value is 0.219. Let me try this again. Once again, the p-value is. So you see, it's saying that it's from the same distributions. Once again, over here, if I make my location 2 extremely close to the location 1, then I have some difference. And let's see if this can actually pick up on that difference. So it missed it just by a little bit. It is not significant in this example, right? So you can keep playing around with this, and at some point you'll see whether it'll. In this now, even though they're different, our samples are just drawn such that it's basically on top of each other, which is why our p-values are not significant, right? Once again, you can start making this stuff significant if you start drawing a lot more samples. So if you have a sample with thousands, like we've got thousands over here, 1,000 over here, right? Then this starts getting significant. You see the p-value is pretty significant, right? So This is the basics of inferential statistics. You can test all kinds of things with this. Like you can have a distribution. You can test if something else is outside that distribution. You can have some sort of a regression, and you can test whether that regression line is different from the correlation can be explained by chance or it cannot be explained by chance. And the basic setup is as I mentioned to you in this talk, which is that you just keep doing the test many times, and you sort of need to find values that are extreme enough that they're different from chance. And this is all that there is to it, really. I hope you enjoyed the talk. Thank you. This notebook should be available wherever you saw the talk. So I'd encourage you to play around with the notebook. Um, and I hope you understand what a p-value is to some extent, what a test statistic is, and how to draw random variables to run these kind of simulations. I hope you understand what this contingency table is, um, how to interpret p-values to some extent, and how the continuous case is a bit different from the the discrete case. Thank you.
So thanks, Eeshan. So we now keep this thing open for questions. Do we have any questions from the participants here, online, offline? Please, if you have questions, you can write it on the chat window, or you have permission to unmute yourself also and ask. So do we have any questions? Yeah. Do we have any questions, please? So these are very basic concepts which, which are used in analysis. Okay. Yeah. So are there any questions? Yeah. Eeshan, do you want to say something? I think people are tired. It's a Sunday morning.
I'm just curious to see what people thought about it, whether they thought it was clear, whether they think I should go over something again.
Yeah, so you could. Oh, okay. This is a very general question. What are the other things to learn in stats for use in astronomy? Oh God, that's a very broad question. Vijender Singh, there are many different tests and different methods used in stats, and in research, like even Professor Sushant Konar was talking about Mihir, who is in stats, because that's why we need to collaborate with them, because we learn a little bit of stats, but we don't know so much of it. And probably there is a large amount of stats techniques which are unexplored by astronomers also, as well as psychologists. So I think that, but what do you think, Eeshan? What do you think are the key things that we need to concentrate on? Yeah.
So on the one hand, astronomy and physics can be pretty deterministic. So you sort of have an equation which tells you what's going to happen next, and everything follows that equation exactly. Statistics is not very useful for things like that. Statistics is useful if you have like a probabilistic claim where you're trying to say something is more likely to happen, or something is related to another thing. So in within astronomy, if you are going across a certain big data set, and you might have these big data sets now, you might start looking for how one variable is connected to another variable. And the moment you start looking for these correlations or regressions, or like in the examples that I showed, these categorical variables or like two different categories and looking at their certain values and trying to see if they're different or not, that's where it'll be useful. It is especially when you start thinking of it as a probabilistic random system.
Yeah. Or like what we had in the previous talk, sorry, there was a plot of magnetic fields versus pulsars. And if you populate it by the data that's available, a simple exercise that was done was in that distribution to actually look for different categories of pulsars by just seeing the plot and looking for clustering within the plot as Gaussians. So you fit it to 4 or 5 Gaussians, for example, and relate those to certain categories of pulsars. That's what was spoken about. So, but yes, there are a whole set of things that can be done. Yeah, but by the way, in Astro we do have a lot of data, so there's no data problem. So you can add.
So statistics also comes in when you have, see, you can't observe every individual pulsar or every individual star. So you just have a sample which you have got, and when you have to check whether the results you are getting, is it a representative of the population or not, right? That's again statistics is used. From the set which you have and the results which you get, you say whether it's representative of the larger population, or you have two different sets and say whether they are similar or not. That's when again statistics comes in. Then small number statistics is another game, and the numbers are small. How do you infer from small numbers? Okay, so statistics is getting very essential in astronomy. Okay. Okay, thank you, Eeshan. You'd like to add something more?
No, I'm good.
Shushan, you'd like to say something on statistics you use in Kolmogorov-Smirnov test and various similar things. Okay, thank you. So let's thank Eeshan and proceed with the next one.
Yeah. So the next